That class thing. Yeah. So, in the example that was given of the 10 kilograms of aluminum cooling, what kinds of conclusions did you draw from that when you saw the way that it was cooling down? Yes?
It seemed to require less energy to get it from really hot to sort of hot, but more energy to get it from sort of hot to room temperature.
Okay, so require energy if you're heating it up, releasing energy if you're cooling it down.
Yes.
Yes, okay.
For me, I didn't talk so much about the energy at each phase, but I was trying to understand like why like specific heat at a higher temperature was more than that at a lower temperature. Same with heat diffusion, it had something to do with the bonds present, like being in a solid state because it's so restricted in movement. It more as energy goes into it, it more directly translates to a change in temp.
Okay.
It doesn't have as much freedom to move.
Okay, and the conductivity is probably better, or I mean the heat transfer once you start to melt it is probably better because not only do you get heat transfer by conduction but also by convection, so it's going to be rolling around inside. So interesting, yeah. Push a little further, good. We assumed that the specific heat was constant over the temperature range. That's false, but it's close enough to use. It changes with temperature change. Anything else anybody noticed about it?
For question 1 or 2?
1 or 2, yes. Yes.
Well, this is like a complete guess, but I think that it's assuming that the block is re-solidifying into one like perfect crystalline structure. It doesn't have like a ton of voids and defects and stuff.
What about the graph do you think is indicating that it doesn't have a ton of voids and stuff?
Would it not have a different rate of cooling if there was like gaps in between it and stuff, or does the voids not really affect that if it's inside of the?
I think the voids are on such a tiny scale that they don't actually matter to it. Yeah.
So it is assuming that it's like all pure aluminum.
Yeah, so I think pure aluminum is one because it has a constant freezing temperature. Does a pure material actually have a constant freezing temperature? Not quite. It actually will change a little bit across there, but good enough for right now and for this graph.
I don't know, like I kind of wondered this, I don't really know what it means, but when you cool something from a super high temperature, the rate of cooling, would it be the same, like rate of cooling from like a liquid to a solid? Would that be the same as going from like, I don't know, it's like 100 degrees room temperature? Would it always be the same rate of cooling?
So the rate of cooling, no, it would not. And that is because radiation. So radiation is just heat leaving the object and projecting to other objects around it. Radiation goes as the temperature difference to the 4th power. And so when you have a very high temperature radiating to room temperature, it radiates very quickly. If you have a low temperature, it radiates much more slowly. So to the 4th power. So radiation is huge. If you are able to do radiation, that's great. In space, that's why they have to rotate things all the time, because the heat energy of the sun is radiating onto one side and the spacecraft is radiating heat to the blackness of space on the other side, and you have to keep rotating it to keep that radiation happening and equalized across the spacecraft. If you don't, bad things happen.
Rotisserie chicken.
It is a rotisserie chicken, and if you're in, or it's a rotisserie, and if you're inside it, you are the chicken. That's right.
No, it's a topher. It's a turducken.
Except you have to put human in there somewhere. Anyway, spacecraft human. Eutectic alloy. Tell me about eutectic alloy and why it might be useful. Yes?
I said that it is, well, it's a type of material that can go from liquid to solid without having to go through the slushy zone.
Okay.
So it phase transitions really quickly at a certain temperature, and then Jake
Yep.
said it might be useful for something like soldering or like electrical components where you're trying to like apply metal to things in a very like specific area and not have like too much flow in between cooling time.
Okay, so reducing the amount of flow, yes. There are also other good things about it for that.
It also has a, on average, a very low melting point, lower than the things it's alloyed with, which allows it to not deform the things you're melting it to, so you can have a metal connection without ever melting. You know, when
Yeah.
you're welding, you melt everything around it too.
Yeah,
You
that's
don't
right.
end up
So
soldering.
when you're soldering, you don't want to melt the circuit board and melt the component. You want that to happen at a low temperature. And it is just crazy to me. I don't know if this strikes you as crazy, but if I take metal A that melts at whatever, 400 Celsius, and I take metal B that melts at 500 Celsius, and I combine them at the right amount, and that combination melts at 300 Celsius. That is bizarre. I could see all sorts of answers between 400 and 500, but for it to melt at a lower temperature, wow, physics. It'll throw you for a loop sometimes. So anyway, that's pretty cool. One other thing that it's used in that you may have, especially if you have a computer that has a little bit higher end processor on it, you will have a eutectic in the heat, a heat pipe that is attached to the processor of the computer. And so what happens is there's a little heat pipe that gets to some radiator fins. Their fins are there to radiate the heat out into the atmosphere, but often right on the chip, right on the processor, it is just too small a space to be able to have enough surface area to radiate well. So often they will put a little heat pipe. So a heat pipe is really cool. It's a tube with a vacuum in it, and it usually has a metal wick that runs along one side. And so what happens is you have heat on one end, and that will take often a sodium mixture with some other things, and it will evaporate the sodium there. So that is absorbing a tremendous amount of energy because you're taking that metal from liquid to a vapor. And so it absorbs a tremendous amount of energy, and then by thermodynamics, it is going to flow to the point in the system that has the lowest temperature, because systems like to equalize the amount of energy. And so it will flow to the place that has the lowest energy. That is the back side of those radiating fins, because they're cold, because they're radiating. And the material will get there, and it will solidify, or not solidify, it will form into liquid, and as it does that, it will release this tremendous amount of heat into those radiator fins, and then it flows back through the wick to the other side. So it's a completely passive system that pumps heat away from where you're working. So that's pretty cool. Often, to get those at the right temperature, because you need it to operate at the temperature of the chip, you would use eutectic alloy to tune that temperature to just the right place. So it almost always is true. You can also use this for collecting heat on giant Stirling engines. Yeah, I don't have a picture of that here. I have a picture of that in my office. But anyway, for tracking solar, you can collect the heat energy and you can create electricity directly, where you can accidentally burn through things. So we used to have these giant dishes. They were about 25 feet across, and when you parked these dishes, they were all mirrored on one side, and they reflected all the heat energy to an engine that was mounted at the focal point. And the problem is what to do when you don't want to collect heat energy, because anywhere you point it collects some amount of sun. So we normally stood them up and pointed them directly north, which is all good until the middle of the summer, when the sun actually rises and sets a little bit to the north of the east-west line. And so when it did that, one day some people were on site and they had parked their rental van off to the side of the dish, and the light came in and reflected off the dish and focused on the side of their rental van and melted all of the plastic trim off the side. which makes it harder to return your rental van, and it's kind of a hard story to explain. No, see, I didn't wreck it, I just parked it. Honest. Okay. Let's talk about this graph a little bit more. I want to talk about what is happening in this area here that's called alpha lead, and this area over here that's called beta tin. So that material that's there is a combination, in this case, it's a combination of lead and tin, but it is in solution. So if this were liquid, it isn't liquid, it's a solid, but if it were liquid, it would be sort of like salt water or sugar water, where the salt or the sugar is chemically bound to the water, and as long as you don't have too much of it, it will be a solution. So it is a different substance composed of the constituents. So this is, if you look at it, it will look all like one material because the aluminum and the tin are bonded together there. It looks like a continuous material throughout this region. When you get into this area over here, you have more tin than is able to stay in solution. So what happens is you have little globs of tin floating around in it, as well as the solution. But remember, this is solid. So the weird thing is that if you have this material fully solid, completely solid, no liquid at all, and you cool the material from this point down to this point. So you're cooling from inside this alpha lead area down here into the section at the bottom that's just labeled solid. Some of the tin will come out of solution. Little globs will just appear in the solid. And so they are getting there by diffusion. They are moving within the structure, so you have this crystalline lattice structure, and the little tin bits are moving through the lattice because they're smaller than the lead bits, and diffusing into little globs. And thermodynamics drives this, that they want to separate and become little globs. But this is amazing to me that you can have the solid metal. You know, if you set a solid metal on the desk right there, you sort of expect that as long as it's solid, it's not really gonna change on the inside. But this is serious changes going on the inside. There are materials that are gathering together, they're moving throughout the structure, driven by heat and driven by thermodynamics. Up here in this section, this is solid alpha lead bits that are floating around in liquid. Over here, beta tin is kind of the same thing. It is mostly tin with little bits of lead. They are in solution in this little tiny region right here. It is in solution. And then if you heat it up more, you get into this beta tin plus liquid. And if you cool it down, you get into this area down here that is just solid material. Yeah, any questions about that? Overall, eutectics are not particularly useful. There are a few instances in which they are useful. We talked about solder being one of them, heat pipes being another. But overall, there are a lot of problems with them that make them difficult to use. One of those is that often they're not structurally very good. This combination of lead and tin, you know, is good thermodynamically. Structurally, it's not that great a material. Cost-wise, they're often not very good to deal with because they have large amounts of expensive materials in them. And so we don't use them a whole lot. We talk about them in this class, and then people get really excited about it, and every time there's a question on casting, they say, use eutectics. And anyway, They're often not that useful. Any questions about that? Okay. Sorry, yes.
I had a question on it earlier. So the alpha lead is where it's solid, like some of it's solid and some of it's liquid, or are you
No.
saying all of it is solid?
In the alpha lead area, everything is solid. So
Even at,
this
like,
is the
300
solidus
Celsius.
line right here that
Oh, okay.
dumps
Okay.
down and across and then goes up right there. I'm sorry, goes all the way across and then up right there. So in this alpha lead area, everything is solid. But it is, if you're in this gray area, it all looks like one material to you. Yeah.
Are we ever gonna need to like, what from this graph are we, for example, for a test or something, like need to memorize or remember?
So I want you to know, I want you to have an understanding of what's going on here, that this area is solid, that this is a solution that is also solid. The understanding that if you move temperature-wise from one place to another, even with a material that is solid, it can change what it looks like inside. We're gonna talk more about that later today. And then it's also important to understand that there are these slushy zones where there is a mixture of solid and liquid. And the slushy zones become really important in casting because next to the walls of the mold are gonna solidify. And understanding this is pretty important because in just a few minutes, you're gonna have to draw one of these.
And then
Yes.
on the end, is that another slushy zone?
The beta 10 plus liquid is slushy. And this area right here is another solution, just like the alpha lead. This beta 10 is another solution area, meaning it is a solid that contains both lead and tin, but if you look at it, it's just gonna look like one material because the small amount of lead is in solution in the tin, the tin matrix. All right. A metal freezes at a constant temperature, indicating that the metal is most likely a solidus line, a eutectic mixture, eutectoid mixture, an allotropic transformation, or a pure metal. Okay, 4, short, excellent. D, 4, yes, pure metal, excellent, good. All right, the key to metallic bonds is eutectic mixing, free electrons, electron sharing to fill outer electron shells, or well-ordered crystalline structure. Some twos? Mostly twos, maybe, yeah, some fours. Anyway, the best answer is probably free electrons. And that is because well-ordered crystalline structure is key to metallic bonds, but it's also key to other things. So it's not unique having a well-ordered crystalline structure. But free electrons are unique, and they are going to become very important later in the course because they allow us to take the material and mush it into a completely different shape and have it still be a metal, not come apart. The rate of diffusion of impurities. So we have these impurities and they're moving through the systems, through the structure. So is that affected primarily by the presence of a slushy zone, a melting temperature of the impurities in the eutectic point, the type of impurities, the crystalline structure in the eutectoid mixture, or the temperature, the percentage of impurities, and the size of the impurities? Okay, some 3s, some 4s, mostly 4s. I think 4 is the best answer. The reason that 4 is a better answer than 3, so certainly the type of impurities and the crystalline structure are not that different than the percentage of impurities and the size of the impurities, so those two are pretty similar, but eutectoid mixture really has nothing to do with this. That is a specific mixture that goes straight from one solid condition to another with a phase change without going through an intermediate phase. So it really doesn't have anything to do with this. So, rate of diffusion. If you have small impurities, they can move through the crystalline structure much faster. If you have higher temperatures, the thermodynamics drive those to move much faster. And the size of the impurities, or the percentage, because they do not like to, well, thermodynamics will drive them together or drive them apart depending on what temperature you have. And so thermodynamics will drive them back and forth. Questions? No. Okay. Match the definitions with the correct terms. So you can hold up the number of fingers for solid line, eutectic mixture, hypereutectic, liquidous line, eutectoid mixture, allotropic transformation, and diffusion. So changes directly from solid to liquid without going through a slushy zone. You have some 2s and some 5s. So this is from solid to liquid, so it is eutectic, number 2. The eutectoid is from one solid to another solid. We won't spend much time talking about eutectoids. That's deeper in the materials noise than we need to go. Transition from slushy zone to liquid. Okay. Some 4s, mostly 4s, some 1 through 5. It is the liquidous line. So the line from something that's partially liquid into fully liquid is the liquidous line. The solidus line is from solid to anything else. And so that is at the edge of the solid zone. Rearrangement of atoms within a structure due to migration of individual atoms. 7, yes, it is diffusion, good. And, whoops. And the change from one solid structure to another is an allotropic transformation. So the fact that it can change structures without melting, this is unique, this is nutty. So anyway, we'll talk about that more. So what I want you to do is, with folks around you at the table, we have this part here and then these 2 parts here. So casting is the process where we melt metal and we pour it into a mold, and then it comes out in roughly the right shape that we want it to be. Roughly, being a good thing. So what I would like you folks at your table to think of are what are advantages to making parts this way and what are potential challenges, and especially when you're thinking about this, think about the metal solidification that we've been talking about. So we don't know all the other things about the processes yet, but we'll talk about that with somebody near you.
You can't do something like rock and roll.